IMG305, Practical Imaging Informatics, Chapter 1, Technology. Okay, so just to begin, I know that this chapter will probably be a review for most of you, but there are some people in this class who may not have the radiology background and they may come from a different background, maybe IT or whatnot, but nonetheless, we'll just review and go from there. To begin, we will start with terminology. In medical imaging, there is a certain hierarchy. It goes patient to exam, series to image. For example, a patient may have a CT exam completed, which is also called a study. The study could have multiple series, which are also called sequences. It could be a set of images with contrast, a set of images without contrast, but essentially a series is a set of images. A series may then consist of a single image or a series of images. Moving on to the modalities. Modalities are basically categorized into two radiation groups, either ionizing radiation or non-ionizing radiation. Ionizing radiation is radiation capable of producing energetic charged particles that move through space from one object to another where energy is absorbed. And since the energy is absorbed, it can be used in a hazardous way if the tech does not know how to use the radiation or if there is too much used. I'm sure you've heard reports in the past few years where dose has really been an issue, especially high dose, and maybe your facility is even watching their dose levels and bringing in your physicist or whoever to be able to regulate those doses. That is all a part of ionizing radiation. Examples of ionizing radiation include general radiography, fluoro, mammo, computed tomography, and nuke med. Examples of non-ionizing radiation include ultrasound and MRI. Moving on, projection imaging is also known as planar or static imaging. An example is just simply a plain X-ray, where radiation passes through the patient, is detected on the opposite side of the body, and produces a 2D image. Overlapping structures can occur in radiography. This is also known as superimposition, and it can make this type of imaging difficult to interpret. It is a 2D image is what your end result is. With tomographic imaging, moving on, this is known as a cross-sectional type of imaging, and it includes CT, MRI, and ultrasound. For example, in CT, the source and detectors actually rotate together around the patient, producing a series of one-dimensional projections at a number of different angles. So it is always taking pictures as it is rotating around the body. And then the data is mathematically reconstructed to produce a 2D image of a slice throughout the body. However, going even further, then the digital geometric processing comes into play and can be used to generate a 3D image. Structural studies are images of anatomy or tissues in the body, and this includes plain radiographs. And then there are functional studies. Functional studies provide images that represent molecular or physiological measures. So an example of a functional study could be an ultrasound, like when you're looking at the blood vessels and how their flow throughout the body is. Another example is a nuke med scan, particularly a thyroid uptake scan. They're injecting the radioactive dye and then seeing where in the body it takes in the radioactive material. Just a few more examples of functional studies are CT and fluoroscopy. Now we're getting into the specific modalities. So now we're going to look at specifically just radiography. In general radiography, grayscale variations of an image represent the attenuation of the density of tissues that are being looked at. So for example, bone has high attenuation, which allows less of the X-ray signal to reach the detector. And air has a low attenuation, meaning most of the X-ray signal reaches the detector. As you'll see with all the modalities, we're going to talk about the pros and the cons. In general radiography, an advantage is that it is simply quick and easy to get a general X-ray. The exams don't take long at all, and they can be performed easily. The equipment also isn't very costly and is widely available. Low amounts of radiation are used, so that is the ionizing radiation that we talked about in the previous slides. General radiography has high spatial resolution, but some disadvantages are that it is hard to visualize the low contrast structures. And we've also talked about the superimposition of anatomy that can occur, which makes it hard for the radiologist to differentiate which structures are which in his readings. And a con, as we said, is that simply it uses ionizing radiation. Although the amount of radiation used is low, the fact that it still uses ionizing radiation can be seen as a con compared to other modalities that do not use non-ionizing radiation. Moving on to fluorography. So essentially, fluorography uses ionizing radiation, and an image intensifier is used to amplify the output image. So in fluoro, a continuous acquisition of a sequence of X-ray images over time is produced, and this results in a real-time movie, also known as a cine loop. The advantages to this imaging modality is that it images anatomy of a patient in motion, so in a real movie, and it also provides real-time feedback during a procedure. So I'm sure you've seen, many of you at least, have seen barium swallow studies where there's actually a movie of the barium going through the esophagus and traveling through, and a radiologist can see right then and there what the problem is and can actually simply just talk to the patient right in the room as it's going on. So the pros is that it uses images in motion and it provides real-time feedback. However, the disadvantage to fluoroscopy is that it produces lower quality images. Since the anatomy is seen in motion, which we all know in radiography, a number one rule is to keep motion to a minimum. Examples of fluoroscopy procedures include barium studies of the esophagus and the GI tract, arthrocentesis studies, and any interventional radiography studies that can be performed in real time. Moving on, we will now talk about computed tomography, or CT. So as I mentioned in a previous slide, CT uses tomographic imaging, where the detectors rotate around the patient using a collimated X-ray beam. In CT, thin transverse sections of the body are acquired in the images, and they represent an absorption pattern. This is also known as X-ray attenuation. Absorption values are expressed as Hounsfield units. They are expressed on a scale of plus 1,000 to negative 1,000. So plus 1,000 range is imaging bone, and the negative 1,000 range is imaging air. So remember, the Hounsfield units represent the X-ray beam absorption of whatever structure they are imaging. Just to have a neutral, water has a Hounsfield unit of 0. So that is, it is always 0 no matter what. It's always the constant. Using CT has a lot of advantages, really. It has good contrast resolution, meaning it allows for differentiation of tissues with similar physical densities. The tomographic imaging eliminates the superimposition of any anatomy. So there is no overlying of the anatomy that happens in CT. Any region of the body can be imaged with CT from head to toe. I'm sure some of you have seen it all. All of these advantages has made CT the actual modality of choice. Doctors like this modality. However, it does have high equipment and procedure costs. But one of the main things also is that CT is prone to artifacts. So they form high contrast objects and make imaging a little more difficult to see. Moving on to another modality, MRI. So MRI is the first non-ionizing modality we're going to talk about. It uses a high-intensity magnetic field, and it utilizes gradient coils that turn radio frequency pulses on and off throughout the imaging process. MRI uses phased array receiver coils that acquire multiple channels of data at the same time. One of the most important things to know about MRI is that it utilizes hydrogen atoms in the body. So the hydrogen atoms are very important in that the MRI forces the atom of fat and water molecules to align with a magnetic field when the radio frequency pulse is turned on. One of the biggest pros to using MRI is that it uses non-ionizing radiation. So, this is good for pregnant women who cannot receive ionizing radiation, It's great for little children who should really have low doses of ionizing radiation at that time in their life. It has excellent soft tissue detail, so the ability to visualize blood vessels without the use of contrast is great. And it does not pick up any bony artifact, unlike CT. But it is especially useful in neurological, cardiovascular, musculoskeletal, and oncology imaging. However, it does have its downsides. One of the biggest things is that MRI is extremely costly. And a lot of times, it's not just the cost that poses a problem of getting the MRI into your building, but the size. Depending on where the MRI is in the image, or in the building where it is located, it can actually be a pretty big feat, knocking down walls and doing other construction projects in order to get the MRI in the building. Another downside is that the scan times can possibly be pretty long. So they're a lot longer than CT, that's for sure. However, like I said, if you have to use non-ionizing radiation, sometimes long scan times is just something you're just going to have to sacrifice. I'm sure you've heard before, or maybe have experienced yourself with an MRI exam and how it can be a little claustrophobic to patients, so it's sometimes intolerable to them. Or it may just simply be intolerable to a patient because it's extremely hard for some of them to lay still and lay flat for long periods of time, especially those with back issues, for example. Also, one of the biggest cons to MRI is that it is very selective on the patients that it can receive. As you know, no metal allowed in MRI whatsoever. And this goes as far as pacemakers as well. So there's actually a pretty low category of patients that it can actually be useful for. However, for those patients that can go to an MRI, it is an extremely useful modality. All right, nuclear medicine and PET imaging. Nuclear medicine and positron emission tomography measure the decay of radioisotopes in the body. So to be more specific, the physiologic, metabolic, and chemical interactions of the radioisotope are measured by utilizing a gamma camera with sodium iodide scintillation crystals. A few pros of these modalities is that it does measure the targeted specific chemical physiologic functions of tissues in the body that we had discussed before. It is particularly useful when looking at infarcts in the cardiovascular system, pulmonary emboli in the lungs, especially if a patient cannot have a CAT scan. Maybe they can't have contrast, which is sometimes a doctor's imaging modality of choice, CAT scan is. But if they can't do that, nuke med is a great second choice. The cons to using nuke med and PET scanning are that they have a high equipment cost. So some hospitals even have a PET scanner that rotates around to each facility, just because they can't facilitate having a PET scanner on site due to the cost. It is often not an exam that can be done in emergent situations due to having to wait on isotopes to be delivered. So again, going back to the pulmonary embolism example, one of the reasons that doctors usually do choose CT for their patient is because it can be done on the fly, it can be done in an emergent situation. However, that is not the same with nuke med. It has to be, there has to be a little bit more planning used in the exam process. All right, ultrasound. Ultrasound uses high-frequency sound waves produced by the transducer that is held in the tech's hand. The transducer also receives the reflected sound waves that travel through the different tissues of the body and are reflected back to it. So it converts the signal into an electric current, which is then produced into a grayscale image that is seen on the monitor. The advantages to using ultrasound is that it is relatively low cost. It uses non-ionizing radiation, which is always a plus, and the equipment can be portable, which is handy in bedside imaging for when a patient is unable to travel down to the department for the exam. So the ultrasound can come to you. It is especially useful when monitoring pregnancies, as you all know, imaging of the child's brain, of a neonatal brain, confirming pleural effusions of masses, and assessing the thyroid, testes, and soft tissue lesions. A disadvantage to this modality, however, is that it is operator dependent. So This means that the results of each exam may vary according to the skills of each technologist. So if you've had a technologist that is highly skillful, you'll probably get great exams, but it could be vice versa for a technologist that maybe isn't as versed. Ultrasound also notes poor visualization of structures underlying air and bone, and is not a good choice for obese patients. This is because the sound waves scatter when they're reflected through large amounts of fat, which then, as you know, reflect back poor images. All right, so I won't touch on this too much just because I know that it is basically a review for most of you, but now we're going to talk about digital images. So a digital image is simply an image that can be digitized, both in space and in amplitude. So it can be considered as a matrix, where the rows and columns are identifying a point in the image. Elements in the digital array of a 2D image are called pixels. So this is an example of a pixel, just this one little square right here. And each of the pixels are represented by a number in the computer. They are also called picture elements. Elements in the digital array of a 3D image are called voxels. So right here, specifically, you can see that this is a 3D image. Voxels are also called volume elements. I suggest referring to figure 1.1 in your textbook for a good illustration of pixels and voxels. All right, in order to be processed by the computer, a digital image must be digitized both spatially and in amplitude, as I previously said. Image sampling is the digitization of spatial coordinates, and it is directly related to pixel size, reflective of matrix size, and affects spatial resolution. Quantization is the digitization of the amplitude, or brightness. It is determined by computer bit depth and is reflected in the image contrast resolution. All right, how is a digital image actually formed? So the process of digital image formation includes 4 key steps, and I laid them out in order down here. In the first process, the analog image must be scanned line by line in order to obtain a continuous analog signal representing the variations in image brightness. Then, on to the next step, spatial sampling must occur. This is the process of dividing the analog signal into individual pixels. It is performed in equal intervals. Then contrast quantization occurs, which is a process that converts amplitude into a digitized numerical pixel value. And finally, the analog to digital conversion must occur. This turns the quantized level into binary code. All right, 2 crucial image quality factors are spatial resolution and contrast resolution. Spatial resolution limits the sharpness in the edges separating objects in the image. It is a function of image sampling, and it affects matrix size. So the more frequent sampling results in smaller pixels, which results in a larger matrix size because they have an indirect relationship. And this in turn generates a higher spatial resolution image. Now, contrast resolution, it limits the differentiation of detail with and between objects, and it is a function of quantization. It is important to remember that the total resolution of a digital image is the spatial resolution and the contrast resolution combined. An image that has poor spatial resolution can be made sharper and have a better detail by enhancing the contrast to get the total result of an image. All right, moving on to noise. This is a characteristic of all medical images. No matter the modality, noise is always a factor. As you know, increased noise equals lower image quality. So if you want a great image, you have to keep that noise to a minimum. It is also referred to as image model and can show up on images as being textured, snowy, or grainy, and this is what degrades the visibility of the low contrast objects. The source and amount are dependent upon the modality, so noise happens in each modality for different reasons. You will see the most amount of noise on nuke med images, and the least amount of noise occurs on just plain radiographs.